Okay guys, welcome back. We are on problem 3 now. Okay, so we have two identically negatively charged spheres x and y having charges of the same magnitude. They are placed 500 millimeters apart in a vacuum as shown in the diagram below. So the magnitude of the electrostatic force that the one sphere exerts on the other is 0 0.22 0.288 newtons. Okay, so now, yeah, as you can analyze this statement, you can see that the charges, they say they are identical, and then their charges are equal, and they are what again? They are negatively charged. Okay, so now they did not give us the charges. How much are the charges? So we are going to have to calculate them. So now 7.1, state Coulomb's law in words. Okay, so when you state Coulomb's law in words, you can first write it with the aid of equation, and then state it looking at the equation. So now what do you say? You say that the magnitude of the electrostatic force is directly proportional to the magnitude of the product of the point charges and inversely proportional to the square of the distance. Okay, so without wasting time, we say magnitude of electrostatic force is directly proportional to the magnitude of the product. The magnitude of the product of the point charge, yeah, is directly proportional to the magnitude of the product between the point charges. Magnitude of the product between 2-point charges. 2-point charges, and inversely proportional to the square of the distance between them. Okay, between them. So now 7.2.1, calculate the charge on each sphere. Okay, so now we know they have told us that Q1 is equals to Q2. Okay, so now I know that I will start by writing Coulomb's law equation like this, so that I will get 1 mark. Okay, so, and I know because of this fact that F is going to be KQ1 in Q1, okay, over R squared. So now what do I want? I want this. So here is the same as I have Q1 all squared divided by R squared. Okay, so if you can check this now, let's make Q1 a subject of the formula. So Q1 is going to be R squared over K multiplied by F, and okay, it will be the square root of that. Okay, because if I multiply both sides by the reciprocal of this, it will remove this. Okay, and then I introduce square root both sides to get that. Okay, so now the square root of R squared, how much is R squared? Is 500 millimeters meters. Okay, so divided by K, 9 times 10 to the power 9 here, multiplied by F, 0,288. Okay, so what is the answer? Q1 is what? Square root of 500 10 to the power minus 3 all squared divided by 9 times 10 to the power 9 times 0,288. Okay, so I have 2.83 times 10 to the power minus 6 coulombs. Okay, so now the charges, I know that is what is Qy and Qx, they are equals to that 2.83 times 10 to the power minus 6 coulombs. So we have answered the question. This is the magnitude of those charges. Okay, so now here they're asking calculate the number of excess electrons on sphere Y. Okay, so we know now that sphere Y has a magnitude of 2.83 microcoulomb. Okay, so now we need to include its charge. Okay, so it's minus 2.83 times 10 to the power minus 6 coulombs. Okay, so in order for us to know how many electrons are in excess, we'll have to use n Qy over Qe. Okay, so this is principle of quantization of charge. I just made n subject of the formula. Okay guys, so now Qy is minus 2.83 times 10 to the power negative 6. Okay, so Qe is elementary charge. Remember, when we are calculating number of electrons, the number must be positive. Okay, so in order for the number to be positive, so now because here the charge is negative, you are going to choose the negative value of the elementary charge. Okay, so we have that you have negative 2.83 times 10 to the power minus 6 divided by minus 1.6 times 10 to the power minus 19. Okay, so what do we have now? We have 1.7 7 times 10 to the power 13 electrons in excess. Okay, so 3 marks, 1 mark here, 1 mark here, 1 mark there. Okay, so now let's do another one. Okay, so here we have a scenario. They put point P here 800 millimeters away from Y. Okay, so now they say define the term electric field in weights. Okay, we've defined it in one of the problems that we've done. So what are you going to say? We know if you want to define electric field as well, you see, you write this E F over Q. So what can you say? You can say that this electric field, you can say electric field at a point is electrostatic force experienced per unit positive test charge. Okay, per positive test charge. Okay, at a point. Okay, so okay, so here. So let's say you started here, electric field at a point. It is electrostatic force experienced per unit positive test charge at a point. Okay, at a point. So what is the direction of the net electric field at P? Choose left or right. Okay, at P. So now we know that X and Y, they are both negative, right? So they are both negative. So now because they are both negative, here the field lines, they go inside. Also here field lines, they go inside. Okay, so from point of reference of P, when I look at here, the field lines, they go away from P. Also these ones, they go away from P. So now it means that they go to the left or westwards. Okay, so the net electric field is going to go to the left. Okay, so the answer will be left. Okay, so now calculate the number of electrons that must be removed from sphere Y so that the net electric field at P is 4 times 10 to the power 4 newtons per coulomb to the right. Okay, calculate the number of electrons that must be removed from sphere Y so that the net electric field at P is that into the right. Remember that now, before the electrons are removed, the electric field is towards the left. Okay, so in order for the electric field to be towards the right, how many electrons must be removed from sphere Y? Okay, so when electrons are removed from sphere Y, it means that this sphere Y, it will be positive, and then it will have a charge that goes towards P, and then it will overpower the electric field at X. So the overall electric field, or the net electric field, it will be towards the right. Okay, so now electrons will be removed, so it must have, we want to know what is the final charge that will give that electric field. Okay, we want to know what is the final charge, of Y that will give that electric field. Okay, so now they say that if this so this is going to be like this, right? So now we have a negative here, now here we're going to have a positive, then here this is P. Okay, so now this one is going to be to the right, this one we know it's to the left. Okay, but then now the electric field must be towards the right, so meaning now the electric field diagram, it will be something like this. This one will be longer and this one will be shorter, so the net electric field will go to the right. Okay, E net will go to the right, so now this will be EX, this will be EY, the new EY again. So now this EY, it will be due to the new charge after the electrons are being removed. Okay, so here we can tell that now, oh, E net will be let's say if we choose to the right as positive, it will be EY minus EX, you see. Okay, so now we understand each other, right? Okay, so I'm proceeding now. E net is equals to EY minus EX. Okay, so how much is EY? EY, it must be given by KQY divided by R squared, right? Minus EX must be given by KQY qx divided by r squared. And remember, this qy is the qf because we're asking how much electrons must be lost. Okay, so after the electrons are lost, there will be a final charge, which is this one. Okay, so now is qyf, okay, after the electrons have been lost. Okay, so now from here I can say inert. They gave us inert. They say inert is 4 times 10. Okay, 4 times 10 to the power 4 Newton per coulomb. Okay, let me not write the units yet. Okay, now is equals to 9 times 10 to the power 9 qyf divided by the distance between y and p. Distance between y and p, 800 millimeters. Okay, so 800 times 10 to the power minus 3 all squared minus 9 times 9 to the power 10 qx. How much is qx? Minus 2.83, okay, microcoulomb. Okay, now 2.83 microcoulomb. This one has not changed. Okay, so then the distance between is that, okay, between x and p is 500 plus 800. Okay, so 1300 millimeters. Okay, so that 500 plus 800, okay, millimeters, which is 1.3 millimeters. Okay, so now here I have 4 times 10 to the power 4, and then 9 times 10 to the power 9 divided by 800 millimeters all squared. So now I have 1.40625 times 10 to the power 10 qyf minus 9 times 10 to the power 9 times 2.83 times 10 to the power minus 6 over 1300 millimeters. Okay, so now I have 15,071.01. okay, so now I'm going to take it to the other side. So 4 times 10 to the power 4 plus 15,071.01. okay, so all divided by 1.40625 times 10 to the power 10 equals to qyf. Okay, so let's press our calculator. 15,071.01 by 1.40625 times 10 to the power 10. Okay, so now qyf, the final charge after the thing has lost the electron, 3.916 times 10 to the power minus 6 coulombs. Okay, so now this is not the charge we are going to use. Okay, so this is the final charge. So we have to know how much charge was lost when electrons were lost. Like we want to know how much negative charge was lost. So we're going to say the change in charge. Okay, so the change in charge is going to be the change in charge of y final minus change in charge of y. Okay, so now this one is 3.916 times 10 to the power minus 6 minus into minus 2.83 times 10 to the power minus 6. Okay, so is equals to 3.916 times 10 to the power minus 6 plus 2.83 times 10 to the power minus 6. So 6.746 times 10 to the power minus 6 coulombs. Okay, so now this is the charge, the change in charge when the electrons were being removed, when the electrons were being lost. Okay, so they removed this charge in order to gain this. Okay, they removed this charge from that to gain this. Okay, so now and then how many electrons were lost? Okay, so I'm going to say N is equals to Q, change in Q divided by QE. Okay, so now you will notice that this is positive charge and it tells us about protons. Okay, so how many electrons are we short of? Are we short of? Are we running short of? So it tells us how many electrons are lost. Okay, so 6.746 times 10 to the power minus 6 divided by positive 1.6 times 10 to the power minus 19. Okay, so 6.746 times 10 to the power minus 6 divided by 1.6 times 10 to the power minus 19. Okay, so how much do I have? I have 4.22 times 10 to the power 13 electrons. Okay, so that much of electrons were lost in order to make that charge positive. Okay, so if I was calculating how many electrons were gained, so this one would be negative and then I was going to divide by negative. So now I'm calculating how many electrons are lost, so this one is positive and then I'm dividing by a positive value. Okay, so I don't think there is a problem that can give you, you know, that can make you sweat after you have understood this. Okay guys, so don't forget to like, share and subscribe, and yes, you can also write in the comment section. Okay, thank you guys, much appreciated. I love you. Also, I'd like to give credits to the volunteers. Everything physical sciences Siyavula. It is helping learners a lot. So I guess I should also link the textbook in the description so that you guys can go and read the textbook on your own. It is very good. Okay, so thank you guys.